Welcome to a video on the top 10 tips, tricks, strategies, and big ideas to help with statistical inference for proportions. So in this video, it's all about inference for proportions, and we're going to really focus on 10 tips to help you understand it. So here we go, starting with number 1. Know the names of the inference procedures. So statistical inference is the procedure and methods of using sample statistics to make judgments about population parameters. So specifically in this unit, we are using a sample proportion to help us make a judgment about a population proportion. That's the whole idea of statistical inference. And in this unit, there are 4 different methods, 4 different procedures that we could use. Make sure you know the names of them. Here they are. A 1 sample Z interval for the population proportion of, and then you're going to fill that blank in with the context, right? So 1 sample Z interval for the population proportion of kids with blonde hair in my school, whatever that may be. Now, an interval is used when we have no idea what the true population proportion is, and we're trying to figure out what an interval for what it could be. Then we could do a 1 sample Z test for the population proportion of, fill in the blank with the context. So a 1 sample Z test for the population proportion of students in my school that do their homework. Now with a test, you have an assumed P. You think you know what the truth is, but you claim that maybe it's higher, maybe it's lower, or maybe it's just flat out something different. And then you're going to actually conduct a test to figure out if that claim or that alternative is true or not. Next one is a 2 sample Z interval for the difference between the population proportion of girls that do their homework every night and the population proportion of boys that do their homework every night. Again, you're filling those blanks in, but here you're doing an interval for what the difference between 2 population proportions could possibly be. And then finally, we have a 2 sample Z test for the difference between the population proportion of black bears that have a disease and the population proportion of brown bears that have the same disease. So again, in a test, you start off by thinking that there's no difference, and then the alternative is, oh, I think black bears are more diseased, have a higher proportion of the disease than brown bears, what have you. But again, these are the 4 different procedures. So anytime you approach a problem, consider how many samples are there? 1 or 2, because that'll kind of cut it in half. Then you got to ask yourself, what am I doing here? Am I finding an interval to try to figure out what that proportion could be? Or am I doing a test to see if a claim is correct or not? That's going to make it a test versus an interval. So 4 different situations. Make sure you know all of them, but really make sure you know the names. Tip number 2, make sure you know how to write the hypotheses for a test, whether it be a 1 sample Z test or a 2 sample Z test. So hypotheses are only needed in a test. You do not need hypotheses for an interval, because in an interval there is no assumption about what is true for the population proportion or for what might be the difference between 2 population proportions. So in a confidence interval, you're simply trying to figure out what is true because you don't really know. All you have is your sample statistics. Whereas in a test, there is some preconceived idea of what could be true, and you're trying to test if it's still true or maybe it's greater or lower. So let's talk about what those hypotheses would look like for a 1 sample Z test. Now in a 1 sample Z test, you're going to read the problem and you're going to see that something is known to be true. Maybe you read that 10% of kids in your school have blonde hair. And you conduct a sample, and your sample data comes back and shows that 12% have blonde hair. So you think, oh, I think that the proportion of kids in my school with blonde hair is more than 10%. So your hypothesis, your null would be status quo. No. The truth is 10%. It's not more, it's not less. It's equal to 10%. That's what's true. That's what I'm supposed to believe, right? And then the alternative is what you're claiming. So I'm claiming that I believe it's higher. So I think the truth is more than 10%. So that would be your null and your alternative hypotheses. Now note that in the hypotheses, you never use p-hat. P-hat is just one of many samples that exist. It should never be used in your hypotheses. Your hypotheses are always using the true proportion, because that's what you're testing, the truth. That's what inference is all about. You're trying to make a judgment about the true proportion. And then again, the 10% is what you believe to be true, but now the alternative is what we're hoping to show, and that it might be more than 10%. Now, for a 2-sample z-test, here you have a proportion from your sample. So maybe from my grizzly bears, we find out that 15% were infected with the disease, and my sample from the black bears had 21% infected with the same disease. Now here, the null that you would assume is that there's no difference. The proportion of grizzly bears with the disease is the exact same as the proportion with black bears with the disease. No difference whatsoever. And the alternative is what we're wondering. Now you got to read the question to figure this out, right? Because maybe the question says, all we care about is that they are different. We don't really care who's higher, who's lower. We just care that the proportion of grizzly bears is not equal to the proportion of black bears with the disease. In that situation, you use a not equal to sign. But maybe you read the question, it clearly says, hey, we believe that the proportion of grizzly bears is less than the proportion of black bears with the disease. Or maybe it says greater than. So read the question to know what sign to put there. So once again, recognize that p-hats are never used in your hypotheses. Your hypotheses are always based on the truths, and when you got 2 samples, grizzly bears and black bears, you have to have a proportion for the grizzly bears and a proportion for the black bears. So that would be my hypotheses there. So be very careful to correctly write your hypotheses, and make sure that you also have the name, which we already talked about in tip number 1, and your name should incorporate what these numbers actually represent. So this would be a 2-sample z-test for the difference between the proportion of grizzly bears that have a disease and the proportion of black bears that have a disease. That way the reader knows what the heck the G and the B stand for when you write this notation. All right, get ready for the next tip. Tip number 3, explaining a p-value. Big idea here because a p-value is a huge part of a test. So, what is a p-value? The probability of an observed statistic occurring or more extreme, given that the null hypothesis is true. So in generic terms, that's exactly what a p-value is. You have an observed statistic. In this particular unit, we're looking at p-hat. So I have a sample proportion. The p-value of that sample proportion is the probability of that sample proportion occurring or more extreme, given that the null hypothesis is true. Now, you got to be careful with that phrase, or more extreme, because it could mean higher, but it could also mean lower. So that's where you have to look at where your sample proportion is. If your sample proportion is on the high side, you want to look even higher. If it's on the low side, you want to look even lower. So the probability, the p-value, right, it comes from the sampling distribution, which is why creating a sampling distribution is so vital to finding a p-value. So the probability comes from the sampling distribution, which is showing the distribution of all possible sample statistics from a sample of a specific size. So let's actually look at an example. So this is an example of a 1-sample test. So let's say I have a null hypothesis that the true proportion of a population is 14. No context there, I know. And the alternative is I believe the truth is greater than 14%. So of course I'm going to go ahead and get a sample. In my case here, I had 75 values or 75 objects, people, animals, whatever it is, and my sample proportion was 19%. Now, once I build that sampling distribution, which is normal, has a center of the assumed truth of 14%, and has a standard deviation, in this case, standard deviation is about 0.04, then I can say, okay, where's my sample? And 19% falls somewhere right around here. Now, a p-value is the probability of that sample statistic occurring or more extreme. Now, why'd I go higher here? Because 19% is already higher than 14%. My alternative is that I believe the truth is more than 14%. So, of course, I'm going to look more. So when I actually go ahead and calculate this, what I'm saying to find a p-value is I'm trying to find the probability that of all possible p-hats, right? This model, this sampling distribution is filled with p-hats. So what's the probability of all those p-hats that one is greater than or equal to mine? That's the mine, 19%. I'm so sorry. That's actually a common mistake that I almost made right there. This is your sample proportion. And that would be all of this probability. Now, of course, if you're wondering how you're actually going to find that, well, you first need to get a z-score, the actual position of this. That's why it's called a z-test. And then you're going to find the probability that your z-score is greater than whatever that particular z-score is. And again, this is just a video go over tips and tricks. I hope you already know how to find that z-score. If you're not, you need to go back and watch some of my other videos. But if we get this p-value, what we're saying is this: of all possible sample proportions from samples of size 75 taken from the same population, the probability that a sample proportion is more than the one we observed of 19% is the p-value. So it's this probability right there. It's the probability of this curve. Now, just looking at this picture, it looks like it's going to be fairly high. The z-score looks a little bit over 1. I don't know, just kind of guessing 1.2, whatever. Just a pure guess there. But again, this looks like it's actually going to be pretty high, which basically tells me that 19% is not significantly high. So I'm probably going to fail to reject the null there, but that's a whole nother tip, trick, or topic. All right, here's an example of a p-value in another one in a one sample test. Same situation, right? Null 14%. Now this time my p-hat is 0.08. So I actually want to point something out here. So think about this for 1 second. The null would be that, hey, 14% is what I read. That's what's going to go in the center. Now, if the alternative was that I think it's greater than 14%, well, I would actually stop. I wouldn't even do this test, because if my sample came back at 8%, that means my sample is not supporting what I believe to be true. In that case, I already know I'm going to be wrong. I already know that my alternative is probably false, and I should keep the null because my sample didn't even support my own conclusion. So in this situation, I would only assume that our alternative would be that the true proportion is less than 14%. So then again, what we're going to do is we're going to locate 8% somewhere right around here, and we're going to find the probability of all possible sample proportions that one would be even lower than mine. So that'd be the probability that of all possible sample proportions, one is less than or equal to the observed value that I got. I would need to get the z-score, because then I could actually use my calculator to find the probability that is below that particular z-score. That's how you find the p-value. One more example here for a 2-sample test. So let's say in a 2-sample test, remember, our null is that there is absolutely no difference between these two proportions. Proportion of bears with a disease, black bears, grizzly bears with a disease, nah, they're all the same. And alternative is, oh no, we think the probability, we think the proportion from population 1 is greater than the proportion from population 2. All right, in this case, to find our p-value, we're going to get our observed difference. So we noticed a 10% difference between our samples. A 10% difference is somewhere right around here. So the probability that any other difference, right, because again, a sampling distribution is filled with possible differences between samples from population 1 and population 2. So the probability that any other difference is more than the one I saw of 10%, that's going to be my p-value. And I'll be honest, in this case, it looks like it's going to be pretty low. But of course, to actually get the p-value, you have to get your z-score, and you can use your calculator. But I just want you to understand what a p-value represents. It's the probability of all possible differences that you're going to find one that's 10% or more, because that's what I observed. All right. That's it for trick. Well, I guess it could be a trick. Tip number 3, hopefully you truly understand what a p-value is. Tip number 4, coming right at you now, when to double the p-value. This is a oftentimes forgotten thing. Kids overlook it, so let's talk about when that p-value needs to be doubled. In either a 1-sample test or a 2-sample test where your alternative hypothesis uses the not equal to sign, that is when you need to double your p-value. So anytime you read the problem and it doesn't say you think the proportion is greater than, or you think the proportion is less than, or you think that one is greater than another, one is less than another, all you care about is that the proportion is not equal to what you thought it was, that's when you double your p-value. So anytime you use that not equal to sign in your alternative hypothesis, once you find the p-value on your calculator, you're just going to simply times it by 2 before you make that decision. So maybe you read a problem and the null hypothesis is that the true proportion is 18%. And the alternative is you don't care if it's more or less. You just care that it's something different than 18%. Once you go through the process, right, you're going to get your sample. Maybe your sample is 29%. You're going to find the p-value, the probability that any other sample is more extreme than yours. Whenever you get that p-value, all you got to do is times it by 2. Multiply it by 2. That's it. That's when you double your p-value. Then you make the appropriate decision for your test. Tip number 5, wording the conclusion to a test. A lot of students know how to do all the steps to a test, but they do a poor job of writing that conclusion. So just know this, the conclusion is all about the alternative. Nobody conducts a test hoping that they're wrong. Every time you set up your null and your alternative hypothesis, the goal is to show, now you don't want to cheat obviously, but you want to show the alternative is correct. So maybe your null is that the true proportion is 10%, and the alternative is that you believe it's actually greater than 10%. Now, you wouldn't even be doing this if you didn't actually believe that the alternative was correct. So the conclusion needs to be all about the alternative. You're either going to claim you have statistically significant evidence that the alternative is true, or that you don't have statistically significant evidence that the alternative is true. Your conclusion is never about the null. Keep that in mind. All right, so what does statistically significant mean, by the way? This could probably be its own tip on its own, or its own trick on its own here. Saying that the results are statistically significant means that the probability of the results were so unlikely that the results could not have occurred by chance. This is why statistically significant occurs when your p-value is very, very low, less than your level of significance, whether you're using 5 or 1%. So when you have a low p-value, what you're saying is that your observed statistic should not have occurred, and it was very unlikely, and it wasn't just because of pure chance, it was because, well, what could be the because? Oh, the alternative is true. And that could be the only explanation, is that the alternative hypothesis is true because what you saw should not have occurred if the null is true. So the explanation is the null is not true, hence the alternative is. So I like to look at the conclusion as a 3-step process. So step 1 is you got to compare the p-value to your alpha. That's going to actually tell you what to do. And you need to do that in your conclusion. Step 2 is rejecting the null or failing to reject the null. When your p-value is lower than your alpha, that's when you do have statistical significant evidence. So you're going to reject the null. And when you reject the null, what you need to say afterwards is there is significant evidence that the alternative is true. Just make sure you say that in context. So I do have significant evidence that the proportion of balloons that deflate sooner than they're expected is greater than 10%. Something along those lines. Now, the opposite of this would be when your p-value is greater than your alpha. Here, well, you're going to fail to reject the null. Here, you're saying that your sample might have occurred by chance, meaning it wasn't weird. So we would conclude by saying there is not enough significant evidence that the proportion of balloons that deflated before they were supposed to is greater than 10%. Do not say the null is true. Don't ever say the null is true. We just don't have evidence to say our alternative is true. That's the key to making a very good conclusion worded in context. And tip number 6, when to use standard error. I call standard error the twin brother of standard deviation, or twin sister if you're a girl. Sorry, don't want to offend anybody. All right, so standard error is used when you have no idea what the true population proportion is, or you have no assumption of what it could be. Now remember, the formula for standard deviation of a sampling distribution for a sample proportion is the square root of the true proportion times 1 minus that true proportion, all divided by your sample size. The standard deviation for the difference between two samples is a giant, huge square root, the P1, 1 minus P1, all divided by sample size 1, plus the true proportion for population 2, 1 minus that proportion, all divided by your sample size. Now again, these formulas for standard deviation require the true P's. Now, if you have no idea what the true P is, nor do you have any assumption of what it's supposed to be, all you have is your P hats, that's when you have to use standard error. Now, this is typically most often going to occur when you're finding a confidence interval, because in a confidence interval, you have no idea what the truth is, nor do you have any assumption of what it could be. So here are the formulas for standard error. Here they are. A little bit of a typo here. Let me fix that. Sorry, there we go. Okay, so for a one sample, all I'm doing is using my standard deviation formula, but I'm replacing the p's with p hats. With two samples, I'm replacing the p's with p hats. That's it. That's when you are using standard error. So the formulas for standard error are the exact same formulas for standard deviation. We're just replacing the p's with p hats. Think of it as the best we could do. We don't have a choice. We can't use standard deviation, so we're going to have to go with standard error instead. Typically, you're using not typically, in any confidence interval, you're going to be using standard errors. So that is when they're most often used. Tip number 7. This is a good one. When to use standard error combined. Okay. Standard error combined should be used in a two-sample z-test for the difference between two population proportions only. In no other situation would you use standard error combined. The idea is that only in a two-sample z-test do we have the null hypothesis that the two population proportions are equal. So if our null hypothesis is that the proportion of grizzly bears with the disease is equal to the proportion of black bears with the disease, then why do we even look at them separately, right? Grizzly bears and black bears, if I'm telling you that it's all the same no matter what, it doesn't even matter if you're a black bear, it doesn't matter if you're a grizzly bears, you got a certain percentage of chance of having the disease, it doesn't matter, then why don't we just put them all together? That's the idea of standard error combined. If we are to assume the null hypothesis is true, then why don't we just combine the two samples together to get one combined sample proportion? So again, you're never going to do this in an interval, and you're never going to do this in a one sample test, because in a one sample you don't even have two of them. You only got one. So this is only used in a two sample z test. Now, how do you actually get the standard error combined? Well, actually, first you have to get the p hat combined. P hat c is what we call p hat combined. So here you're going to add in the denominator your two sample sizes together. So maybe you have a sample of 200 and a sample of 300. So now you got 500 total. And then you're going to put all of your successes from sample 1 plus all of your successes from sample 2 together, getting you one giant p hat. Now, please be careful. I'll get some kids that have a p hat sample 1, a p hat from sample 2, and they'll take the average to get the p hat combined. No. Don't ever take an average. What you got to do is literally got to put all of your successes together in the numerator, all of your total sample sizes together in the denominator to get your p hat c. Then we technically have two formulas, but they are the same. I'm going to prove that to you in 1 second here. So notice the numerators are exactly the same because right? Isn't that the null? That they're the same? The two proportions are the same, right? So for the first sample size, we use p hat c and 1 minus p hat c, and the second sample is supposed to be the same, right? So we use p hat c and 1 minus p hat c again. Now, this is the formula that I believe is actually on the AP Stats formula sheet, but you might see this formula as well, maybe even a multiple choice or something. Think about it. If the numerators are both the same, you could technically factor that value out. It's still inside the square root, and then you're left with 1 over sample size 1 plus 1 over sample size 2. It's just another way of writing it. Either one is going to be full credit if you were to actually do it on a test, and that's how you get your standard error combined. Either one of those formulas works, no problem. They're technically, again, algebraically equivalent. Now, I do want to talk about this. Listen, if you don't use standard error combined in a two-sample z-test when you're supposed to, maybe you just use regular standard error. Let me write the formula for this real quick. It would be p hat 1 times 1 minus p hat 1 divided by sample 1 plus p hat 2 times 1 minus p hat 2 divided by sample 2. You would actually still get full credit. So you could not use standard error combined, maybe because you forgot or you were lazy or you just didn't know when you were supposed to do it, and you did use regular standard error. The difference between the two is very negligible, and it's not enough that's going to make your conclusion completely wrong. But it is correct. You are supposed to use standard error combined. Now, here's the one place where it's tricky. In a FRQ, I'm not going to take off any points, nor the AP Stats test, if you forget to combine, even though you're supposed to. But if it's a multiple choice and it's saying, hey, what's the standard error for this 2-sample z-test? And they have the standard error combined and the regular standard error, the one choice that's going to be correct is the standard error combined for a 2-sample z-test. Please keep that in mind. Getting close to the end here. Tip number 8, know type 1 in type 2 error, be able to explain them in context and understand the consequences. So type 1 error is rejecting a null hypothesis that is really true. The null hypothesis is true, but you reject it. That's obviously an error. So again, anytime a null is rejected, there is a potential of a type 1 error. You're not going to be asked, did you make a type 1 error? Did you not? Because that's not a question I could ask you because you don't even know. It's the idea that anytime you reject a null, you hope you're doing the right thing. You're basing your conclusion on your p-value like you're supposed to, but there is a chance that the null was actually true and it should not have been rejected, resulting in a type 1 error. The probability of a type 1 error is alpha. So you do choose your significance level by choosing a significance level of 0.01. You do have a lower probability of a type 1 error. Now let me explain this real quick. So if here is my sampling distribution and my null is that the true proportion is 14% and the alternative is, I think it's greater than 14%. Now, if I'm going to choose a 5% alpha value, now a 5% alpha value might be something up here in this top 5%, right? So that top 5% is what's going to cause me to reject. But if I'm not supposed to reject, then that means there's a 5% chance that I do reject when I wasn't supposed to. So that's why alpha is the probability of making a type 1 error. Now, obviously, you hope that you're still doing the right decision, so it's not like I could say, did you do it, did you not? It's really just a matter of understanding the potential that anytime you do reject a null hypothesis, there is a chance that you did the wrong thing. A type 2 error is not rejecting a false null. Should be a T right there, not rejecting a false null. So here, the alternative hypothesis is true, but our p-value tells us to fail to reject the null. So our conclusion is that we're going to, I guess for lack of a better, actually I shouldn't say that. I was going to say keep the null, but we never want to word it that. We just fail to reject the null. But no, that was wrong. The alternative hypothesis is really true. So anytime you fail to reject a null hypothesis, there is potential of a type 2 error. Because maybe you should have rejected the null and gone with the alternative because it's actually true. Same thing I got done saying a moment ago. I'm never going to ask if you did it or didn't do it. It's just a matter of anytime you do a test, you get the p-value, you decide to fail to reject a null hypothesis, there should be this little inkling in the back of your mind that, maybe I made the wrong decision, and that would be a type 2 error. Now, the probability of a type 2 error is beta. Calculating the actual value of beta is outside the scope of this class, but that would be beta. Now, let's go back to this example again here, where our null hypothesis was that the true proportion is 14%, and the alternative is that we believe the true proportion is greater than 14%. So once again, if we set our alpha value at 5%, that means the top 5% right over here is going to cause us to reject the null. So the idea is that if we fail to reject the null, maybe our sample comes over here and we're like, that sample has a high p-value, we're going to fail to reject the null. There is a chance that we were wrong because maybe, just maybe, the truth was, let's just say the truth was 19%, right? The truth was 19% and the real sampling distribution, the correct sampling distribution is centered around that 19%. So that is where you're like, 19% is more than 14%. I should have rejected the null, but my sample just based on it being a not that weird of a sample told me otherwise. So again, type 2 error, the probability of it happening is beta. Don't worry about calculating beta. Just understand that type 2 error is the alternative is what's actually true, but for whatever reason, no fault to us, our conclusion told us to fail to reject the null. That is a type 2 error. Tip number 9, power and how to get it. So what is power? Power is the probability of correctly rejecting a null hypothesis that's false. So if the null hypothesis is wrong and the alternative hypothesis is true, and we conclude that we have evidence to reject the null and go with the alternative hypothesis, that's having power. So power is the complete opposite of type 2 error. Because remember, type 2 error is the alternative is true, but we don't conclude that and we fail to reject the null. Power is the opposite of that, which means if beta is type 2 error, then 1 minus beta equals power. So once again, in this course, we're never going to worry about actually calculating beta, which means I'm never going to actually ask you to calculate power because you would need beta, but I can ask you about power and how to get more of it. Now, the easiest way to get more power is increase your sample size. Bigger samples will also be closer to the truth with less variation. So if the alternative is in fact true, a bigger sample will make it easier to see that. Again, small samples have huge standard deviations, which means that you might get something really, really high, or you might get something really, really low when it's not really, really high or really, really low, okay? So small samples allow for a lot of weird things to happen, which could lead to a lack of doing the right thing, which is a lack of power. So bigger sample sizes will give you more power. Now, another way to get more power is to increase the level of significance. Now, let me explain this. The level of significance is alpha. Typically, we might use a 1% alpha or a 5% alpha. But if alpha goes up, then the probability of type 2 error goes down. With a higher alpha, you'll be more likely to reject the null. Now, let me explain this real quick here. So if our null, once again, is that the true proportion is 14%, and the alternative is that we believe it's greater than 14%. Now, if I use an alpha of, let's say, 1%, now that means that only in that top 1% am I going to reject the null. So in this case, think about it. If the alternative is true, and it's actually the true proportion is more than 14%, then in this situation, I only have a 1% chance of seeing that. I only have a 1% of samples are going to cause me to reject the null, which are going to make me go with the alternative. But if I increase my alpha to, let's say, 5%, that would be, let's say, somewhere right around here maybe. Okay? So that means now I just made the probability of me rejecting the null higher, because now I have a 5% chance of getting one of those really, really high samples that's going to show me that the truth is clearly more than 14%. So if I want more power, increase your level of significance. Now you might in turn say, well, wait a minute, doesn't that give you a higher chance of type 1 error? But remember, type 1 error, the null is true. We're not even in that realm of a situation right now. We're in a situation where the alternative is true, and that's what we want to show. So that is why raising alpha will give you more power. Now, another way to get more power is when the actual truth is further from the null. Hence, our sample statistics should be as well. Now, think about this for a second. Go back to the same problem we've been talking about. The null is that the true proportion is 14%. The alternative is that we believe the true proportion is greater than 14%. If the real true proportion was 15%, that's only a little bit more. Technically, it is more, so the alternative is true, because that's what power is, the alternative being true. But since it's only a little bit true, only a little bit higher than 14%, it might be tougher for me to see that. Whereas if the true proportion was, say, 36%, that is so much higher than 14% that I would assume a large amount of samples are going to show me that. You can actually think about this on a number line. If here is the null, 14%, and we build our sampling distribution around it. If the truth is way over here at 36% and the sampling distribution is built around that, sorry for my terrible drawing, then you think about it, if this is what's really true, then I should get samples that are up here because that's what's really true. And those samples are all very far away from 14%. Hence, I would reject the null and go with the alternative. But if the truth is only 15%, and my models actually overlap a little bit, that means that yes, I might get a sample near that 15%, but because samples vary, that could actually tell me that 14% could still be true, and I wouldn't reject the null that needs to be rejected. So another way to get more power is to live in a world where the true proportion is way higher than what you thought it was, in particular this case. Now, let me just quickly say here, if the alternative was less than, then I'm looking for something like 1, 2, 3, 4%, way less than 14%. That's again going to give me more power. So it obviously does depend on the direction of your alternative. And finally, the last tip in this video, what does 95% confident mean? Spent a lot of the tips talking about ideas for tests, but confidence intervals are also really important, but they are really easy. But a lot of times kids are confused about what 95% or 99 or 98 even means. So let's talk about it. Now, oftentimes this is a follow-up question to a confidence interval. Explaining the meaning of 95% confidence is actually not part of the 4 steps to conducting a confidence interval. But it could be used as a follow-up question. Maybe somebody says, hey, can you please explain what is meant by saying 95% confident? Now, here's what it's not. It's not a probability. I'll get a lot of kids that say, oh, there's a 95% probability. No. Or I'll get kids that say it's 95% of the time. It has nothing to do with time. It's not like it happens in March, but not in February. Or, hey, there's a 95% chance. No, not a chance. Or kids that will say, oh, there's a 95% of the truth being in the interval. There's a 95% chance the truth is in my interval, 5% chance it's not in my interval. No, 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 no. Please do not select any of those answers or write any of that down. Here is what it is. 95% confidence relates to the fact that 95% of all possible sample proportions are near the true population proportion in the middle. It's all about that sampling distribution. Any of those samples that are in that middle 95% would create an interval that will contain the true proportion within it. So the best explanation you could give if you're asked to explain what 95% confidence is listen, if many, many, many other sample proportions of the same sample size taken from the same population were found, each sample proportion would create its own interval around itself. 95% of all of those intervals will contain the true population proportion. So it's not about 95% of time or chance or probability. It's about 95% of all possible intervals that are going to contain the truth. And I'm just hoping that mine is one of them. Obviously, that means 5% of intervals will not contain the truth. So here is that idea. If we think about a sampling distribution and smack dab in the middle is the truth, but we don't know what it is. But we do know that 95% of samples are going to be roughly from here to here. That's that middle 95% of all samples. So any sample in that middle 95%, maybe this sample right here, this hat right here, would create an interval around it that, voila, captures the truth. Maybe our sample is here. When we build an interval around our sample, voila, the truth is captured. So any sample in that middle 95% will create an interval that contains the truth. And I believe my sample is one of those 95%, well, because 95% is really high. The only type of sample that would not contain the truth would be one of these really, really high or really, really low samples up here or down here. So if my sample proportion was up here, when I build my interval, notice the truth did not get captured in my interval. But this type of sample way up here is very unlikely, and I don't believe in those unlikely samples from occurring. That's why I'm so confident that my sample is one of the ones in the middle that will contain the truth in the interval. All right, hopefully you enjoyed the top 10 tips, tricks, strategies for inference procedures for proportions, and hopefully it makes you better at it.